Hey there, calculators. Welcome, welcome, welcome back to a new unit. Chapter 5 is kind of interesting in that we've been talking about derivatives and slopes and tangents for essentially the entire class so far. And we're going to flip that on its head now and start talking about area, and specifically in this section, area under curves. You might be a little bit confused because right now it says 5.2. We actually take the book sections out of order. So the first section we're going to deal with out of our textbook is 5.2, and then the next video that I'm also going to do for you is in 5.1. Doesn't really make a difference for you, just as you do your assignments and your readings and things like that. Make sure you are going in the proper order and following your teacher's instruction. We're going to go through this video guide together. I'm going to go in detail, so if I, for whatever reason, am going too slow for you, feel free to tap that speed up, or if you want to pause and work on your own and then zip through my solutions to see if you're right, that is an option. But that is all up to you. What you see on this page here are actually 3 different graphs, and we are going to be using these, what we call integral expressions, to calculate the area under the curve. And when we say area under the curve, we mean the area between the function and the x-axis. So for instance, this first graph here, we're going to label this y equals f of x. The integral expression says I want to find the area under f of x from x equals 2 to x equals 9. So what that means, what this expression means, is I'm going to draw a line from my curve to the x-axis at 2, and I'm going to draw a line from my curve to the x-axis at 9. And my job is to find the area. Well, that is not a normal, basic, traditional shape, this weird little rectangle slanted line thing. However, we can break it up into manageable shapes, and that is what we do with compound shapes. You've done this back in geometry, is we break this up. So I am going to, and you are totally able to do this, break this this compound shape into what I would say, or would call, like more basic or simpler shapes, like rectangles and triangles, like I've done here. And then what we're going to do is we're going to find the area of each smaller shape, add them all together, and that will be our answer, or our equivalent number to this integral expression. So I'm going to just do that real quick. Rectangles, remember, are base times height. So my first rectangle has a base of 1 and a height of 3. So the area of this rectangle is 3. We're going to add to it the second rectangle, base of 2, height of 6. 2 times 6 is 12. Now, this second part, from x equals 5 to x equals 9, you could either treat the way I've done it as a rectangle and a triangle, or technically that's a trapezoid, so you could do it that way too. I'm going to do it the way I've broken it up here. So I have a rectangle with a base of 4, and a height of, it looks to be 2.5. So 4 times 2.5 is 10. And then my triangle here still has a base of 4, has a height from 2.5 to 4.5, so a height of 2. Don't forget that your triangle is half of a rectangle, so its area formula is 1/2 the base times the height. So 1/2 times 4 times 2 is 4. And in order to do that, I just add those numbers up together. This is a relatively simple and clean answer. It is a positive integer. We get 3 plus 12 is 15, plus 10 is 25. I get 29. So my answer to the integral expression given up here, of the integral from 2 to 9 of f of x dx, is 29 units squared. Remember, this is area. Our units should be square units. Perfect. We can get a little fancier in this second graph. We're going to call this y equals g of x. And we're going to assume that the first part of this graph from 0 to 4 is a semicircle. We're going to assume that that area below the x-axis is a triangle, and from 8 to 10 is a triangle as well. You'll notice our left bound is 0, and our right bound is 10. I didn't have to draw a line at 0 because my graph has an endpoint at the origin, or my interval does at least. So here we go. We have 3 separate shapes. We're going to calculate the area of each shape just like we did up above. There's a couple differences here though. Number 1 being from 0 to 4 we have a circle. We actually have a semicircle, so that area is 1/2 pi r squared. Our radius is 2. So 1/2 times pi times 2 squared is 2 pi. And when I do these problems, and you'll do a lot more of these problems with Miss Gogarty in 5.3, I actually just like to write the area in that section. Before I do any problems, I look at my interval and I go for it, and I find each area. What we are going to be doing down here, though, with this triangle, is we are looking at an area below the x-axis. And it's important to know that if my area resides above the x-axis, it is a positive area. This triangle resides completely below the x-axis, so it is going to have a negative area. And I know that negative area sounds strange, but as we get farther into the unit, you will see that that has a definite context that will be important for us. It doesn't change how we find the area, though. This triangle has a base of 4 to 8, a base of 4, and a height of 2. You might even want to call that -2 to help you remember. That's one way to do it. But then it's 1/2 base times the height, so 1/2 times 4 times 2 is 4, but because this is an area below the x-axis, we are going to subtract 4 from our positive area of 2 pi. And then finally, we have our traditional right triangle here. So this is 1/2 base times the height, base of 2, height of 2, 1/2 times 2 times 2, and it's above the x-axis, so it is a positive 2. Unless you are in a situation where you're given answer choices that are decimal approximations, you want to be giving exact answers in these problems. So that means we're not going to estimate pi to 3.14. We're going to just say 2 pi is its own term. So when I simplify this, my area from 0 to 10 under the curve of g of x is going to be 2 pi minus 2. And it is okay to leave it just like that. Beautiful. And these 2 problems are perfect examples of finding the exact area under a curve. And that's wonderful. But I hate to break it to you that most of the curves or functions we're dealing with aren't made up of circles and rectangles and triangles. Often they are curves that look like this. And here is where we get into trouble because the integral expression's meaning does not change. I am looking for the area under this curve from x equals 1 as my left bound to x equals 9, which is my right bound. But I've never been in any sort of geometry class where they teach me to take the area of something so smooth and fluid as this shape. And that's where we have problems. But that's also where calculus comes to help. So there's a method in calculus that says, well, just like we couldn't maybe necessarily find the area in one fell swoop of these first 2 functions, is there a way to break up this function here, function h, we'll call it that, into smaller, more manageable pieces? Maybe even pieces that we can find the area of. Well, there is, and that's what we're going to be spending this unit doing. And so what the prevailing mathematicians of the day, namely Newton and Leibniz, who were the kind of the founders or inventors or discoverers, depending on which word you want to use, of calculus, they said, hey, what if we broke this function up into subintervals, ideally equal ones, and estimated the area? And so what they would do is they would take these into rectangles, like so. And while obviously this area is not perfect, it is certainly going to get us closer than just randomly guessing. And so they would build these rectangles, and they would say, well, this area comprised of these rectangles, I know that's not exactly right, but I know that it's close. And just like maybe your favorite infomercial would say, someone else would say, there's got to be a better way. And maybe you see what the better way might be, and that is, well, what if we just increased the number of subintervals? And so that's what people did. They said, okay, instead of the 8 rectangles I just created there, what if I created maybe twice as many, or 3 times as many, or 4 times as many, or infinitely many rectangles? And that is what we're going to show here eventually. Let's say they started creating rectangles of varying heights down to the x-axis, and the more rectangles they created and then they filled in those areas, the closer and closer and closer and closer they got to the actual area under the curve. And that is actually, you may have been asking, what this little piece means. That dx is basically representing the width of our rectangles. In a perfect world, we're using an integral and calculating an exact value, and the width of our rectangles is infinitely small. We are not there yet. What we're going to do on the next page is use 4 subintervals, a manageable number so you're not spending hours upon hours of your homework, and we are going to calculate the area, or estimate, I should say, the area under the curve, the same curve we've been talking about, in 4 different ways. We call these Riemann sums. You're going to learn more about that as we go. And these are actually approximations. So when I say the left-hand sum or the right-hand sum or the middle sum or even a trapezoidal sum, we're going to talk about what that means right now. So here we go. A left-hand sum means we're still evaluating the same interval, and we need to know how many subdivisions we're looking at. 4, and it says equal width, so the way to break up the interval from 1 to 9 into 4 subintervals is to make our subintervals a width of 2. And we're going to use this same amount of subintervals on every single picture here. And that is the one thing in these pictures that is going to remain the same. After that, it's a little bit different. Very rarely in a calculus situation will you be asked to find 4 different sums, but you will be asked to find either a left sum or a right sum or a middle sum. And so I'm going to show you how to do all 4 on the same function, and then you can extrapolate this and apply this to your problems that you might be working on. So I'm going to zoom in on the left-hand sum here a little bit. I want to still keep my table of values up there in play so I can make sure that I am doing everything I can to make this as visually good for you. So we are going to do this. When I ask for a left-hand sum, what that means is I'm going to start on the left-hand side of my interval and use that height, sorry about that, that height for my rectangle. No matter how good or how bad of an estimate that is. And it's going to look something like this. And if you want to very, very lightly shade those rectangles in to show what you're doing, that would be smart. Now, it is pretty obvious by looking at this picture that my answer is not going to be a great or a perfect approximation. But again, if we increased the number of subdivisions or subintervals, we increased the number of rectangles, we would get better and better and better results. So here is what and how we would write this. We're going to say the interval from 1 to 9 of h of x times dx. Be careful with your notation here. This is approximately equal to. And if it's a left-hand sum, we write L and the number of subintervals 4, which is equal to, and we're going to find the area of each of these rectangles. What we need from our table are the y values of these left-hand sides. And then each rectangle has a width of 2 units. So here's how I would write this out if I was showing my work either for my teacher or for the AP people as they grade. I would say my L4 is equal to the base times the height, which is h of 1, 1.008, plus my base of 2 times h of 3, which is 0.920, plus my base times the height of my third rectangle, which is h of 5, which for my table is 2.420, plus the base of my fourth rectangle, always 2, or at least always the same as the others, and that has a height of h of 7, which is 2.532. If we're using decimals, it is totally okay to use your calculator, and that's what I'm going to do right now. I'm going to type this into my calculator of 2. And apologies, feel free to zip through to the end. I'm just typing this into my calculator now. Two times 2.532, and I get an answer of 13.76 units squared. Now, you might be wondering what it looks like for the others, and that's what we're going to work on. But if you feel you have a good grasp of this, or you want to try and guess what the other sums look like, you may totally pause this and zip to the end of where I'm working at that. But if you would like to see every single graph, and I suggest you do if you're having trouble, that would be what we're going to do next. So here we go with the right-hand sum. Same thing, except now I am going to be pulling from the right-hand side and drawing over my rectangle. The right-hand part of the rectangle, no matter how good or how bad, and I mean bad by like how inaccurate an estimate it might be. Because again, I'm not going to make you do a problem with 100 rectangles. That would be sadistic and awful. But here we go. Same thing. We are going the integral from 1 to 9 of h of x dx is approximately equal. If this was a right-hand sum, I'm going to say r sub 4, and that is equal to, our rectangles still have the same base, and here we go. So we're going to still start from the left-hand side, so this is 2 times f of 3, which is 0.920, plus 2 times f of 5, which is 2.420, plus 2 times f of 7, which is 2.532, plus 2 times f of 9, which is 2.870. 0. And so again, I'm going to type that into my calculator. And we are going to get a little bit different number here. We are going to get 17.484 units squared. And I'm going to leave it up to you whether or not you decide that that number is more accurate or less accurate than the left-hand sum. But you can see that we are definitely calculating a different area here. Okay. Now, when we start looking at a middle sum, that is where we get to be a little bit, have to be a little bit more careful. And so what a middle sum means is that if I have these rectangles from 1 to 3, and 3 to 5, and 5 to 7, and 7 to 9. Instead of using the left hand or the right hand sum, I am going to use the number in the middle. And so that looks a little bit different. So when I draw these rectangles, I am finding f, or h of 2, I should say, and going from there. H of 4, and going from there. H of 6, going from there, and H of 8. Doesn't matter if I'm over or I'm under. These Riemann sums give us an estimation. So let's try here. From 1 to 9, H of x times dx. That is approximately equal to our middle sum with 4 subintervals, which means our base of 2 times our height of 1.427. That's right here. Plus our base of 2 times our height at 4 of 1.773. Plus 2 times h of 6, which is 1.878. Plus 2 times f of 8, way up there, at 3.379. And again, you're going to use your calculator, you're going to type this in, and it's important to note that if you are showing your work here, you need to write out these sums. It is not acceptable, especially on the AP test, to just write M4 equals some number. It doesn't work that way. They want to see what sum you are setting up. And so it is important to write it out, just like I have done here. And again, I am just popping these numbers into my calculator. Two times 3.379. And here, my M4 becomes 16.914 units squared. And again, I'm leaving it up to you to determine which one you think is more accurate, but you will see, because we are only using 4 rectangles, it is certainly not perfect. Awesome. Now, a trapezoidal sum is just a hair different, and that's what we're going to be focusing on here. And so what a trapezoidal sum is exactly what it sounds like. We are connecting our left-hand side of the rectangle to our right-hand side of the rectangle and actually building these trapezoids. Now, some of these look a little more rectangular than others just because we have some close data points. But it's important to note that there is some level of slant here to these lines, some level of slope. And so we are going to kind of fill these in. And you might argue that that seems to be a little bit better of an approximation, especially as our curve slopes upward and downwards. So here we go. We are going to say from 1 to 9 of h of x dx is approximately equal to a trapezoidal sum with 4 sub-intervals. And what we're going to do is remember the trapezoid's area formula. So the area of a trapezoid is essentially the average of the bases, or add up base 1 plus base 2 times the height. Trapezoidal sums are a little funny though, because we were talking along the x-axis, the height in this case is actually the 2, the width of the rectangle, and the bases are the vertical sides. So what we can do here is do a little bit of factoring. We know that we're going to be taking 1/2 times each of these rectangles times the height, which is 2, times the sum of the bases. And so we're going to have to use our table and zoom out a little bit here. So our first rectangle has bases of f of 1 and f of 3. So 1.008 plus 0.920, and we're going to add to that 1/2 times 2 times 0.920 plus f of 5, which is 2.420, plus our third rectangle, which is 2.420, plus h of 7, I should say, 2.532, and finally our fourth rectangle, and what happens in this particular problem, which is kind of nice, is that the 1/2s and the 2's cancel each other out. So I really just have to add up these 8 values, and that's what I'm going to do on my calculator right now. So 1.008 plus 0.920 plus 0.920 again, plus 2.420 plus 2.532 plus 2.532 plus 2.87. And in this situation, I am getting an estimation of 13.202 units squared. Now, my friends, we have reached the end of this problem. You'll see a bunch of problems like this on your 5.2 problem set. Very rarely, if at all, will you be asked to find all 4 sums. But what you will be specified is which type of sum, left, right, middle, or trapezoidal, and you will be told how many sub-intervals. And that is what you are looking for in order to find these. I hope you found this video informational. I hope this worked for you today, and it's been a pleasure speaking with you again. If you have any questions, please email me or your teacher, and we'll talk to you soon. Have a great one, everybody. Thank you for being here. Bye-bye.